Hello everyone, this is Jingyu. I will present my final project of this class, which is the topic related to muons. We have briefly discussed the muon in the class. Today I would like to introduce you to more properties of muon as well as some ongoing muon experiments for supporting my claim that studying muon is the key to understand the standard model in particle physics and even search for new physics. My claim for this project is that studying muons have become the frontier for many particle physicists to understand standard model and possibly unveil the new physics law. In the next 10 minutes or so, I will first briefly introduce you to the history of discovering muons and some basic properties of muons. Then let's review the standard model and beyond the standard model that we talked about in this class. Next, I will illustrate why scientists choose muon for studying the standard model and searching for new physics. Lastly, I will talk about two ongoing muon experiments that scientists are doing for searching new physics. Muons were first discovered by Carl Edison and Seth Nethermeyer at Caltech in 1936 when they were studying the cosmic radiation. They observed that this particle has the same negative electric charge as an electron, but has greater mass than an electron and less than a proton. Later on, the existence of muons was confirmed by J.C. Street and E.C. Stephenson's cloud chamber experiment. Today, people understand that muon is a second-generation lepton with a mass that is about 207 times greater than the electrons. Like the electron, muons are spin 1/2 particles that obey the quantum electrodynamics, and they can interact with other particles through the electrodynamic and the weak forces. Unlike the fairly stable electron, its heavy cousin muon is an unstable elementary particle with the 2.2 microsecond lifetime. Here shows you two decay mode that muon has. Another interesting fact is that muon has a property called spin, which makes them behave like tiny magnets. The magnetic moment can be written as mu equals g times E over 2 mcs, where g is the proportionality constant between spin and magnetic moment. The standard model predicts that g for leptons, such as electron and muon, should be exactly 2. When g is not exactly equal to 2, the particle is processed by an anomalous magnetic dipole moment, which indicates that there is something happening beyond the standard model. The anomalous magnetic field of muon is described here in the formula of A sub mu, which is how much g differs from 2. Because of this interesting magnetic spin property, scientists actually use muon to study the g factor in order to search for new physics. In the next slide, in the later slide, I will talk about a muon G-2 experiment. Okay, the standard model. The basic category of elementary particles are quarks, leptons, and some force carrier particles such as W and Z bosons, photon, and lastly, the Higgs boson that brings mass to all the particles. Even though the standard model is currently the best explanation for properties and interactions of thousands of existing particles in our universe, it appears to be incomplete, such as when scientists try to unify the gravity with electroweak forces. They encounter many difficulties. As the standard model becomes incomplete, scientists try to find new physics that can explain the many mysteries behind particle physics. Over the past few decades, scientists are searching for it if there's any undiscovered principle in nature, such as exotic particles, new symmetry, or new physics law. The search of new physics is called a beyond standard model. One of the most promising aspects of beyond standard model is to search for charged lepton changing flavors. Quarks can change from one type to another, so can neutrinos from the neutrino oscillations. The electron and the muon, together with a third particle called tau, are types of leptons, and the difference between them is referred to as flavors. The standard model does not permit leptons to mix with each other or change flavors. In order to search for new physics, scientists want to find the charged lepton changing flavors. In other words, the phenomenon called lepton flavor violation. Here are some lepton flavor violations equations, such as the muon decay into a positron and a photon. It violates what the standard model predicts. For comparison, the top right equation is not a lepton flavor violation equation, since muon decays into a positron and two neutrinos are just a common weak force decay. Therefore, muon as a second-generation lepton is a great candidate for studying lepton flavor violation. Another aspect of searching for new physics with muon is to study its anomalous magnetic moment, as I stated before. In the muon G-2 experiment, scientists believe that muon is constantly interacting with virtual particles surrounding it that pumps in and out of existence. The fluctuating cloud of virtual particles which modify the G-factor of muon are beyond prediction of the standard model. The last picture shows the G-factor's experimental result from the G-factor's theoretical result that is predicted by the standard model. The standard deviation of the two values of G-factors is 4.2 sigma, which is pretty significant to indicate something unusual happening, such as new physics. So, in a summary, why do scientists choose muon to study the standard model and search for new physics? Well, first, among all the particles, muons have a relatively long lifetime, 2.2 microseconds, which allows scientists to make precise measurements of its property before it decays into electron and two neutrinos. Second, muons are easier to be generated in the accelerators as they are products of pion decays. Third, muons, the second heaviest building blocks of the matter, are 207 times more massive than electrons. The heavier mass of muons make it easier to be detected. Fourth, like electrons, muons act like a little tiny internal magnet. In a strong magnetic field, as it wobbles, all the direction of the muon's magnetic processes. This intrinsic magnetic field property allowed us to study the G-factor of muons and test the validity of the standard model. In general, muons are a great tool to study lepton flavor violation possibility and the G-2 experiment. Finally, muons are a type of leptons which can be used to study lepton flavor violation. Now let's look at the muon G-2 experiment. The left picture shows you the muon G-2 ring at Fermilab. In this ring, the muon's spin caused the particle to wobble or to process a circle. The muon G-2 experiment is designed to study the uncertainty of muon's G-factor, which is slightly greater than 2, in order to find any inconsistency with standard model prediction. The first muon G-2 result announced by Fermilab this April is consistent with the result from previous Brookhaven National Labs muon G-2 experiments. Here's a Twitter of Fermilab a few weeks ago when they announced their experimental result. Scientists at Fermilab find that the combined result from Brookhaven National Lab and Fermilab has a standard deviation of 4.2 sigma, which they say is a strong evidence of exciting new physics. Although the virtual particle explanation can lead us to some exciting ideas such as supersymmetry particles or dark energy particles, some scientists still cast doubt on statements such as physics is breaking or we have found evidence that new physics must exist. First, the 4.2 sigma standard deviation, which is less than the standard deviation 5 sigma, fits an unclear zone of to announce the existence of unknown physics. Second, another hypothesis states that the consistently appearing virtual particles are particles and their antiparticles. Although they both interact with magnetic field and affect the G-factor, the effects of the virtual particles and their antiparticles can annihilate and cause no deviation for G-factor. The details of what happened around the empty space is still unknown. However, the 4.2 sigma and the rigorous investigation still suggest to us the possibility of finding new particles or new interactions such as the supersymmetry, dark matter, and heavy neutrinos. Muons still act like a window into the subatomic world and play a key role in better understanding the standard model and searching for new physics. Next is the mu-to-E experiment. As its name suggests, the experiment tends to find a muon to electron conversion, although the super rare process is like finding a needle in the haystack. Muon to electron conversion is not a traditional weak force decay, but a lepton flavor violation phenomenon as I explained to you before. It is central to understand what physics lies beyond the Standard Model and helps clarify how particles created at the beginning of the universe broke down into stable lighter particles. In a nutshell, muon has played a significant role in particle physics for studying the Standard Model and the search for new physics. The measurement for G-factor in muon's magnetic moment and the search for lepton flavor violation in muon decay show strong hints for a phenomenon beyond the Standard Model. Muon experiment will continue to help study the Standard Model and beyond the Standard Model in the future. Here's my reference for this project. Thank you so much for your listening and patience.